Every second, the Earth traps more solar energy than it radiates back into space. This growing surplus is the Earth's energy imbalance, and it dictates the trajectory of our climate. This stacked area chart quantifies that surplus over 50 years. The energy absorbed by land masses, ice caps, and atmosphere combined accounts for 10% of the retained heat. The remaining 90% is stored in a single repository, the world's oceans. We measure global warming by the daily, highly visible spikes in atmospheric temperature, but the air around us holds only a fraction of the planetary thermal load. If the oceans were to release even a small percentage of their stored heat, surface temperatures would immediately become lethal. The oceans must contain this energy without raising their own surface layers to the boiling point. The atmosphere is merely the symptom. To accurately model the survival of our surface climate, we have to isolate how this 90% heat sink actually operates. Incoming solar radiation constantly bombards the ocean's surface. Water possesses an exceptionally high specific heat capacity. It requires an enormous amount of physical energy to raise its temperature by even a single degree. But sunlight cannot penetrate the entire ocean. Solar radiation and direct atmospheric heat exchange are strictly confined to the top 100 meters, a distinct layer known as the photic zone. The thermodynamic capacity of this shallow surface layer cannot account for 90% of the Earth's excess heat. The ocean must be mechanically forcing the energy downward. Heat does not distribute uniformly through water. The ocean is vertically stratified, structured by rigid physical boundaries. This 3D cross-section isolates the ocean's temperature profile. The sunlit top 100 meters sits directly above a vast near-freezing column. Plotting temperature against depth reveals a sharp plunge just below the surface. This steep gradient is the thermocline. Simultaneously, surface evaporation leaves behind saltier water at the top. Plotting salinity reveals an inverse relationship, a steep structural gradient known as the halocline. When you combine the temperature and salinity drops, they form a solid density boundary slicing horizontally across the water column, the pycnocline. Warm, buoyant water sits on top, dense water sits below. Beneath this density barrier lies the abyssal ocean, a massive volume of water permanently isolated from the surface, locked between -2 and 5 degrees. The pycnocline acts as an impermeable physical wall. Heat cannot passively diffuse through it. To store the global thermal load in the abyss, the ocean requires a planetary-scale mechanical pump. That pump is the thermohaline simpuration, a global conveyor belt driven by heat and salt. This thermal image captures the gradients driving this pump. The warm orange Gulf Stream collides with freezing northern shelf waters. As surface water moves poleward, it carries massive heat north in these circular eddies. When this tropical water reaches the North Atlantic, freezing air drains its heat into the atmosphere. As these polar waters freeze into sea ice, the ice crystals reject the heavy salt brine, expelling it directly into the surrounding liquid ocean. This localized combination of extreme polar cold and high salinity forces the water to its maximum density. Unable to maintain its position above the pycnocline, this hyperdense water collapses under its own weight, plunging down to the abyssal plain. This vector map plots the Atlantic Meridional Overturning Circulation, or AMOC. You can trace the red surface currents pushing north, shedding their heat, turning dense blue, and sinking. Once at the bottom, this water creeps along the global ocean floor. It will take hundreds, sometimes thousands of years for these cold, deep currents to circulate back to the surface. By physically dragging warm surface water north to be cooled, densified, and sunk, the AMOC functions as an active thermal sequestering engine. It hides the globe's excess heat in the deep ocean. But the ocean's heat regulation is not an isolated mechanical loop. It operates through continuous, dynamic feedback with atmospheric pressure systems. This diagram of the Birkenes feedback model illustrates that relationship, using the equatorial Pacific as a baseline. Atmospheric pressure gradients generate trade winds. These winds scrape the warm surface water westward, displacing it across the ocean basin. This displacement creates a physical void in the eastern Pacific. To fill the gap, near-freezing abyssal water is forced to upwell. The presence of this cold, upwelled water suppresses regional atmospheric convection, halting cloud formation over the cold zone. By suppressing convection, sea level pressure rises in the east. This high pressure feeds right back into the Walker cell, strengthening the initial trade winds that started the cycle. Planetary heat regulation relies on this precise alignment of water density, ocean currents, and wind pressure. It is a highly sensitive, self-reinforcing mechanical engine. That mechanical engine is now absorbing a thermal load it was never designed to handle. Returning to our 3D column, we observe the effects of a century of heat absorption. The red surface layer physically expands, experiencing thermal bloating from excess radiation. As the surface heats, the temperature gradient across the boundary mathematically increases. The thermal plunge becomes steeper. The result is a hyperstratified upzone. The pycnocline thickens, becoming an increasingly impenetrable physical wall. This hyperstratification severely limits deep water circulation. When surface water is too warm, it remains too buoyant to sink. Even at the freezing poles, the amok begins to stall, and upwelling mechanisms lose their force. Without the mechanical force of vertical mixing, the ocean's layers permanently stabilize. Turbulent surface waters settle into sluggish, distinct horizontal bands. A hyperstratified ocean chokes the planet's primary heat pump. The conveyor belt that dragged heat into the abyss loses its momentum. The survival of the atmospheric climate is dependent on these deep water mechanical pumps operating beneath the surface. Looking at our energy imbalance chart projected forward, the consequence of a stalled ocean pump is immediate. The atmospheric sliver expands rapidly as the ocean loses its ability to pull heat downward. When the ocean repository reaches its structural limit, the future thermal energy load has nowhere to go. It is forced directly back into the atmosphere. In a permanently hyperstratified state, the ocean hits a rigid physical limit. It can no longer sequester the imbalance. Earth's thermal stability depends on the mechanical movement of deep water. If that movement stops, the heat remains at the surface.